Fundamental of all initialization declaratives is the defined byte instruction, which is written as dB. This is a dB instruction that allocates 1 byte of memory and stores the value 100 in it. Of course, the value 100 written as hex is 64, so this declaration has exactly the same result. And a hex value of 64 is the ASCII code for the lowercase character d, so this is another way of writing exactly the same thing. And you can include a number of bytes in one statement by separating them with commas. This is 3-letter D's in a row, a string. Or you can put a string together with quotes, and you could even mix them in the same statement. Notice that the string ABCD is not a character constant in this case. It's not reversed because it's being declared right in memory, not something to be loaded into a register. The assembler takes care of this for you by deciding when to reverse things and when not to. Just remember that the values in the registers are the opposite order of those in memory. And you can make the same type of declaration, strings and all, with the DW, define word directive. The only difference is that with DW, 16 bits is allocated, so you always get an even number of bytes. If you declare an odd number of initial values, as in this case, one more byte with a value of 0 will be added at the end. You can do the same thing with DD, which declares double words. It will pad the end of whatever you declare with up to 3 bytes of zeros, as many as it takes to fill out a multiple of 4 bytes. And then there is DQ, which will fill out with 0 bytes to a multiple of 8 bytes, or 64 bits. One important note here: if you include more than one value on a line with the values separated by commas, each one will be filled out to the minimum length, and you can get a lot of zeros interspersed in your data. There are 3 more. DT is an 8-byte double real, DO is a 10-byte extended real, and DY is a 10-byte BCD declaration. These 3 will be covered in the upcoming chapter on floating point numbers. You don't always have to specify the initial value. This pseudo operator reserves space. This example creates a block of 22 bytes with no particular initial value. There are reserve operators for other sizes also. This RESW example reserves 1 word of space. RESD declares space for the specified number of double words. There are also reserved declarations for RESQ, REST, RESO, and RESY. You can use these to declare arrays. Most of the time you use one of these, it has a label on it, so it becomes a named variable. There is one declaration pseudo-op that is so unique that it could be your entire reason for using assembly language. Imagine this situation. You have an image file, a JPEG or a GIF or an audio file or some other kind of binary file, and you'd like to include it unchanged inside your program. Well, you can do that with a statement like this. This includes the binary file unmodified as a block of bytes inside the program. By default, the entire file is included, or you can, by appending a number on the end of the declaration, skip a block of bytes at the beginning of the file and just include the rest of it. Or by appending 2 numbers, you can skip some bytes at the beginning and limit the overall size. In this example, the limit is to 512 bytes. And there is a way of declaring names in a program that comes in quite handy. This is an example of an equate. It defines the word level as being the same as the constant value 34. Now it doesn't declare any storage, it just tells the assembler to remember the name and the number. After this, every time you type the word level in your program, it's the same as if you had typed the number 34. And there is another meaning to the $character. The dollar, when used alone in an expression, has a value. It is the address of the current location. So an equate like this has the same value as a label would have at this same location, and you can use dollars in expressions. The address of the beginning of the string is subtracted from the address of the first byte after the string, so the resulting value of the equate is the length of the string. Doing things like this prevents having to count the characters, and if you change the string, the value of the length will change automatically.